And now I have a t-score that is going to be my critical value that I'm going to be able to use to compare my test statistic with. Okay, so remember, if my test statistic is farther to the left than my critical value is, then I reject my H sub O. But this is not nearly as far to the left as this one, therefore this is not in the tail. It is not in the rejection region, so we would fail to reject, and we would, see, they're showing you where the test statistic is, and they're showing you where the critical value is, so we would fail to reject on this one. And that is the same thing we did when we did it with the p-value. Okay, so now the confidence interval method, again, I'm not going to worry about confidence interval method. We're just going to skip this. This is not going to be on your test, so we're going to skip this one. And this one is just another example. Okay, and another example. So here they're doing, on this one's good because they're doing the p-value and the critical value, and we're not going to worry about this confidence interval. They're trying to compare the different ways to do this, so I would run through this one on your own and just look at it, but we're not going to worry about that confidence interval method, okay? And then, according to the p-value, so it says the p-value of 0.0000 is less than, so the p-value is going to wind up being in the tail. And then the critical value is way far to the left of the test statistic is way far to the left. So again, we need to reject H sub O. We're not going to do this one here. So we are definitely going to reject the H sub O because both of these that we know how to do were way far in the extreme. Okay, so just skip the confidence interval, not worrying about that one. So now we're moving into hypothesis testing for the mean when we have large samples or when the sigma is known. So a large sample can warrant the use of the standard normal. When sigma is known, can warrant the use of standard normal. The reason this one warrants the use of standard normal is as samples get very large, the sample standard deviation much more closely approximates the population standard deviation. So in either case, we can use the standard normal. So here, our test statistic is going to be a z-score. You've seen that before. Our p-value is going to be provided by technology, or we can use the area under the standard normal table because we do have an area now. And the critical values, we can use our standard normal table. Okay, so here, oops, I'm going backwards. That's not what I want to do. Let me get back to where I am. Okay, so here's our little cheat sheet here. And again, this should look very familiar. We've got our X bar is our test statistic. We state our H sub O or our H sub A. Our qualification is that sigma is known or our sample size is large. Our population is normal. We have our standard error, which is going to go into our formula for our critical value, our standardized test statistic. We're going to find the area that corresponds to z. So that would be our p-value here. Okay. And then find the p-value for the left-tailed test and for a right-tailed test and for a two-tailed test. And then we can also use critical values if we want to. This one is specifically for p-values though. And we're going to make a decision. We're going to reject H sub O if the p-value is less than or equal to the alpha, because then it's in the tail. Otherwise, we're going to fail to reject. And then we're going to interpret this decision appropriately. Okay, so finding the p-value and using p-values to make a decision. After determining the hypothesis test standardized test statistic and the test statistic's corresponding area, do one of the following to find the p-value. If the area is in one tail, or the left tail or the right tail, we're just going to compare the area with the p-value. But if we have the p-value, if we have the two tails, then we're going to have the p-value twice the area in the tail, so that we double it. Remember, when we have the area in two tails, our alpha is cut in half. So basically, we're going to double that to compare it back to our alpha. So decision rule based on a p-value. If the p is less than alpha, we're going to reject the h sub o. If the p is greater than the alpha, we fail to reject. So less than or equal to alpha, we reject. Otherwise, we fail to reject. If we have two tails, we double it before we do the comparison. So the p-value for a hypothesis test is 0.0237. What is your decision if the level of significance is 0.05? Well, the p-value, 0.02, is less than. Therefore, we're going to reject h sub o. Okay? But if we use the criteria of 0.01 for our alpha, then the 0.02 is not less than, and we would fail to reject at the 0.01 level. Okay, so here it says find the p-value for a left-tailed hypothesis test with a test statistic of negative 2.23. Decide whether to reject h sub o if the level of significance is alpha equal to 0.01. All right, so when we go and look at our standard normal table in the back of the book, and we go and we look at negative 2.23, which is our z-score, we find that the area to the left is 0.0129. So that is the value that's to the left of that. So now we're going to compare that. Is it greater than or less than the 0.01 they tell us to compare it to? And it is greater than, so we will fail to reject. It's only when the p-value is less than our level of significance there that we reject. Okay, so it says find the p-value for a two-tailed hypothesis test with a test statistic of 2.14. So when I go look at the chart under 2.14, which is on the right, then I'm going to get 0.9838. Okay, so 0.9838 is to the left. But now I want what's in the right. So I'm going to do 1 minus that, which is going to be 0.0162 that's in this tail. Since this is a two-tailed test, I need to double this value before I compare with my alpha. So when I double this, I get 0.0324, which is less than that. So now I will reject my h sub o because it is less than that. So this is just practicing, so that you have practiced enough to know what to do in every case. In auto racing, a pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds. A random selection of 32 pit stop times has a sample mean of 12.9 seconds and a standard deviation of 0.19 seconds. Is there enough evidence to support the claim at 0.01? Use a p-value. Okay, so now we're going to use the p-value instead of our critical value. They're claiming that the mean is less than 13, and our x bar seems to agree with that. when we do x bar minus the 13, we divide by our standard error down here, we get negative 2.98. Okay, so negative 2.98, when we look at our standard normal table, negative 2.98 is going to have 0.0014 in the tail. Okay, so 0.0014 in the tail. And this is a left-tailed test, so I do not double it. I compare that to our 0.01, and 0.0014 is less than 0.1, which means I reject H sub O, and the H sub O was not the claim. Since I reject it, then I could say I support the claim. All right, so at the 1% level of significance, you have sufficient evidence to support the claim that the mean pit stop time is less than 13 seconds. Okay, National Institute of Diabetes and Digestive and Kidney Diseases reports that the average cost of a bariatric weight loss surgery is $22,500. You think this information is incorrect. You randomly select 30 bariatric surgery patients and find that the average cost of their surgeries is $21,545 with a standard deviation of 3,015. Is there enough evidence to support your claim at alpha is equal to 0.05? Okay, so the claim is that it's not equal to 22,500 because they were saying it was equal to 22,500, so you're just saying it's not. Okay, so alpha is 0.05. Here's our test statistic, negative 1.73. They want us to use a p-value. So we're going to go to negative 1.73 on our standard normal, and we're going to get 0.0418. So here we go, 0.0418, but since this is a two-tailed, because of the not equal to, we have to double that value, and we get 0.0836. Our alpha is 0.05. Our p-value is greater than our alpha value, and therefore we will fail to reject. Since we fail to reject that one, then we will have to stick with it. So at the 5% level of significance, there's not sufficient evidence to support the claim that the mean cost of bariatric surgery is different from 22,500. So here is your little cheat sheet for your standardized testing using rejection regions. So this is using your critical values instead of your p-values. So again, we're going to do that using the same method we've done before, using our standard normal table to calculate a critical value and then a test statistic. If the test statistic is in the tail, which is defined by the critical value, then we have to reject H sub O. Okay, so let's look at this one. Our rejection region, or our critical region, the range of values for which the null hypothesis is not probable. So that's the definition of what a rejection region is. If a test statistic falls in this region, the null hypothesis is rejected. A critical value z sub 0 separates the rejection region from the non-rejection region. So that's what a critical value is. It separates from your rejection to your non-rejection region. So we're going to find critical values in a normal distribution. We specify the alpha. We decide whether we're talking about a left test, right test, or two-tailed test. If it's left-tailed, we're going to find the z-score that corresponds to the area of alpha. Okay, right-tailed, 1 minus alpha. And then two-tailed, we're going to find the z-score that corresponds to 1/2 of alpha and 1 minus 1/2 of alpha. It's the same thing we've been doing before. The alpha has to be split between the two tails. Okay, we're going to sketch our graph. So here's an example. Find the critical value and the rejection region for a two-tailed test with alpha is 0.05. Since it's two-tailed, the alpha 0.05 must be split. So we're going to have 0.025, and that's going to be on the right, and then we're going to have the 0.025 in the left as far as the alpha, or the area and the tails. So now let's go and look at this. So we're going to have the 0.025 over here, the 0.025 over here, and then that together makes the 0.05. So this in the middle is going to be 1 minus alpha is 0.95. And the rejection regions are to the left of, so that's going to be negative 1.96 and 1.96 positive. All right, and so if you look at your chart, okay, right here, we've got negative 1.9. We follow it across till we get to row 6 right here. And we're going to go 1.96. And guess what it has? 0.025 as the area under the curve. Okay, so that's on the left-hand side. That's the negative z-score chart. So then I go look at 1.96 on the positive z-score chart over here. And 1.9 is right there. I'm going to go across till I get to the 6, which is right there. And the area to the left, trying to get close enough, is 0.9750. You subtract that from 1, and guess what you get? 0.025. Isn't that really, really cool? All right, so that's how we're going to find the critical values there. Just look up the area that you need in the chart, because we are now using standard normal. Okay, to use a rejection region to conduct a hypothesis test, calculate the standardized test statistic Z. If the standardized test statistic is in the rejection region, then we reject H sub O. If it's not in the rejection region, then we fail to reject H sub O. So there's our rejection region in blue. If the test statistic winds up in here, we reject H sub O. If it winds up over here, we fail to reject H sub O. Okay, so testing with rejection regions. Employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is $68,000. I'd like to be making $68,000. A random sample of 30 of the company's mechanical engineers has a mean salary of $66,900 with a standard deviation of 5,500. At alpha is equal to 0.05, test the employee's claim. Okay, so the claim is that the mean of their company is less than 68,000, and there's our level of significance. And since we have a 0.05 and it's a left-tailed test because of the less than, then we're going to have all of our 0.05 in one tail. When we look at our standard table to figure out what is the area that has 0.05, what's the z-score that goes with that, it's negative 1.645. So then we're going to find our test statistic, which means we're going to calculate that. We get a negative 1.10, which is not in the rejection region. Therefore, we will fail to reject the H sub O. which means that we have enough evidence to support the claim. Okay, so there's not enough evidence to support the employee's claim. So we fail to reject, which means that the claim that is less than, we're going to, since we failed to reject this one, that means we basically think it's true, which means that this one is not supported. So at the 5% level of significance, there is not sufficient evidence to support the employee's claim that the mean salary is less than $68,000. So my brain is fuzzy with this cold. I'm sorry, I'm making some mistakes here, but I'm just about finished with 8.3. Then you'll have everything you need to do to master Section 8. The U.S. Department of Agriculture claims that the mean cost of raising a child from birth to age 2 by husband-wife families in the U.S. is $13,120. Okay, to age 2, that's expensive. A random sample of 500 children aged 2 has a mean cost of $12,925 with a standard deviation of 1,745. At alpha is 0.10. Is there enough evidence to reject the claim? Okay, so the claim is equal to. So we're going to have to do a two-tailed test here. So we're going to have an H sub A is equal to, H sub O is equal to, but an H sub A is not equal to, which means we have two tails. Our alpha is 0.10, which means we're going to have 0.05 in each rejection region. So we get 0.05 here, 0.05 here. We're going to end up, remember the z-score that goes with 0.05 was negative 1.645 and positive 1.645. So then we calculate this one. We get a negative 2.50, which is in the rejection region. Therefore, we reject H sub O, which was the claim. At the 10% level of significance, you have enough evidence to reject the claim that the mean cost of raising a child from birth to age 2 is equal to $13,120. Now, these are just some cool ones that I saw on the internet. Sunbathing, is it safe? You wish to sunbathe 30 minutes on vacation on a beautiful sunny April day. You know that UV radiation of 100 is damaging and potentially causes cancer. You are able to find radiation readings on the weather station and decide to sample 64 radiation readings from this locale during April's past and present. You find that the X-bar of these 64 measures is 98.6 with a sigma of 7. Is sunbathing safe in April in this area? Okay, so we set it up. We define our H sub O as mu is greater than or equal to 100, bad, okay? And then we define our H sub A, the mu is less than 100, good. So we're going to, our alpha here, since we don't have our alpha specified, they didn't tell us, we're going to use 0.05, okay? That's a very, now here it says, what would type 1 error be? Okay, and a type 1 error is when you have H sub O and you think that H sub O, okay, so basically dangerous, they list it here, dangerous UV levels exist, but you reject that and you go sunbathing and you get cancer. Okay, so that's a pretty serious consequence. That would be a type 1 error. And type 1 errors are going to happen if your alpha is too large. Okay, because your alpha is your probability of a type 1 error. So maybe in this case you want to make your alpha smaller. A type 2 error would be that we think that the UV levels are actually safe, but we think that they're dangerous, and we don't go sunbathing, but stay in and have a pity party, missed out on the fun. Okay, so we lose the fun day, not a hugely serious consequence. So the beta is the probability of a type 2 error. So we might want to let our alpha be smaller and our beta be bigger just because of the seriousness of getting the cancer. So because it is so serious to get cancer, we're going to make our beta a little bit bigger, and we're going to go all the way down to a 0.01 for our alpha to reduce the risk of making a bad decision in that direction. Okay, so now this is just kind of a very crude picture of what's going on. This was the projected mean. The 100 is that critical value that's going to give us skin cancer. So 98.6 is the X bar. We're trying to find out what is this rejection region and where are we actually on the scope of things here. So let's look at, we're always going to assume that our X bar is true. I mean our H sub 0. We want to find the z-score, and we can use the standard normal distribution in this case because we had a sample size of 64 is greater. So basically our sample size is large, 64, and therefore we can use our standard normal. We're going to take our X bar minus our mean, and then we're going to divide it by this standard error here, and we're going to get negative 1.6. Okay, now the negative 1.6 is the z-score that is our test statistic. So now we've got to figure out what do we compare that to. Okay, and the p-value that goes with negative 1.6 is 0.0548. We can get that from our standard normal table. So now remember, if our p-value is larger than our alpha, and our alpha is 0.01, then we fail to reject our H sub O. Okay, so we fail to reject our H sub O because our p-value is greater, and p-value not inside the rejection region because the p-value is greater than 0.01. Therefore, we fail to reject our H sub O. And remember, our H sub O was the greater than, so here we go. There is not enough evidence to suggest that the level of UV radiation is safe. Therefore, we're going to have a lousy day and stay inside and not get to go outside. But that is, we've decided that that is more important than risking the cancer. Okay, this one is the last example on the slide. It's talking about determining whether an oven is cooking appropriately, and so basically the average temperature in the oven is set to 350, should be 350. Assume that we know the sigma, the standard deviation, to be 1.4 degrees. So because we know sigma, we can use our z-score. We collect 19 samples of oven temperatures when preheated to 350, and we get an X bar of 349.54. Is my oven off target? Okay, so we never discussed whether this was approximately normal or not. So we only have 19 samples. Unless we fix these problems, we can't do this problem with the tools that we have available. We have to have it stated that it is approximately normal, and they did not state that. So we're going to change the 19 to 49, which is greater than the 30, so that we can do this problem. Okay, so now we've got my very crudely graphed, so we're assuming the mean is 350. The 0.05 is our alpha. Because we're saying the mean is 350, or the mean is not 350 is our alternative hypothesis. We're going to split our 0.05 into two tails, and those will be our rejection regions. Okay, so then we're going to come along here and calculate our z-score. Our z is negative 2.3. Since this is a p-value, we want to look, so basically if we, that's our critical p-value here, we can look at our negative 2.3 and see what is the p-value that goes with negative 2.3. And when we get that, we get a p-value of 0.0107, which we will then double because it's in two tails, but it is still less than 0.05, which means we are in the rejection region, which means we reject H sub O. And since we reject H sub O, we reject that our oven is on target. Okay, since we rejected H sub O, we will write our interpretation of the results to say our data shows that the oven is not cooking at an average temperature of 350 degrees when set at 350 degrees. So your oven is bad. And here is the screen that has your homework for all three parts. Now, that means that for all of 8, your book homework is 1, 2, 3, 4, 5, 6 problems for the entire Chapter 8. But please do remember that you do have your online homework, and your online homework is all there. So please get busy. This is Mrs. A, and may God bless your day.